Picture this. 5 kilometers beneath the Pacific Ocean, in crushing darkness where the pressure could flatten a human body in milliseconds, lies a 2,500-ton nuclear submarine filled with Soviet secrets. Now, imagine building a ship so massive, so technologically advanced, that it could reach down into that abyss, grab that submarine like a mechanical god, and pull it up into its belly without anyone knowing. This isn't science fiction. This is the story of Hughes Glomar Explorer, the most expensive lie ever told. Welcome to Never Built, where we explore the technologies that pushed the boundaries of what seemed possible and sometimes broke them entirely. I'm your host, and today we're diving deep into one of the Cold War's most audacious engineering marvels. If you're fascinated by the intersection of espionage and engineering, make sure to subscribe and hit that notification bell. And as we journey through this incredible story, I want to hear from you in the comments. What do you think drove these engineers to attempt the impossible? March 8, 1968. The Soviet nuclear submarine K-129 was on a routine patrol mission in the North Pacific, carrying 3 nuclear ballistic missiles and a crew of 98 men. What happened next would set in motion the most ambitious intelligence operation in human history. At approximately 8:20 a.m. local time, something went catastrophically wrong. The submarine, a Golf-class ballistic missile boat, suffered what Soviet records would later describe as an internal explosion. In reality, it was likely a battery malfunction that triggered a chain reaction of disasters. Toxic gases flooded the compartments. The submarine's electrical systems failed. Emergency procedures that should have saved the crew instead sealed their fate. Within minutes, K-129 was plummeting toward the ocean floor, 3 miles down into the Hadal-Pelagic zone, where sunlight has never penetrated, and the pressure reaches 700 times that at sea level. The 98 souls aboard never had a chance, but their deaths would inadvertently trigger the most expensive intelligence operation in American history. The Soviets searched frantically for their missing submarine. They deployed their entire Pacific fleet, combing thousands of square miles of ocean. But the Pacific is vast, and the submarine had sunk in waters so deep that even their most advanced sonar couldn't penetrate to the bottom. After weeks of searching, they gave up. K-129 was lost forever, or so they thought. What the Soviets didn't know was that the United States Navy had been listening. The sound surveillance system known as SOSUS was a network of underwater microphones stretching across the ocean floor, designed to detect Soviet submarine movements. On that March morning, SOSUS had picked up the sounds of K-129's death throes. American analysts knew exactly where the submarine had gone down, but knowing where it was and actually reaching it were 2 entirely different problems. The submarine lay at a depth of 16,800 feet, deeper than Mount Whitney is tall. The pressure at that depth would crush a human body instantly. No submarine in the world could dive that deep and return. No crane could reach that far down. No technology existed that could recover something so massive from such depths. Yet the prize was too tempting to ignore. K-129 carried nuclear warheads that could reveal Soviet weapons technology. Its communication equipment contained encryption codes that could unlock years of intercepted Soviet messages. Its navigation systems held details of Soviet submarine patrol routes and safe havens. Most importantly, the submarine's nuclear reactor and weapon systems could provide invaluable intelligence about Soviet nuclear capabilities. The CIA understood that whoever controlled this submarine would gain an unprecedented advantage in the Cold War. But first, they had to figure out how to steal a 2,500-ton submarine from the bottom of the ocean without anyone noticing. The solution would require the largest covert operation in CIA history, the most advanced ship ever built, and a cover story so audacious that even Howard Hughes thought it was crazy. This is where our story really begins. Because what happened next would push marine engineering to its absolute limits and create a ship so advanced that its technology wouldn't be matched for decades. The Hughes Glomar Explorer wasn't just a ship. It was a floating impossibility designed to do something that had never been done before and might never be done again. What do you think? Could you imagine keeping such a massive secret while building the most advanced ship of its era? Let me know your thoughts in the comments as we dive deeper into this incredible story. By 1970, the CIA had assembled a team of the brightest minds in marine engineering, nuclear physics, and covert operations. The project was given the codename Azorian, and its mission was simple in concept but staggering in execution. Build a ship capable of lifting a nuclear submarine from the deepest parts of the ocean. The first challenge was purely mathematical. K-129 weighed 2,500 tons when it was operational. After 2 years on the ocean floor, it would be filled with water, potentially doubling its weight. The ship they built would need to lift at least 5,000 tons from a depth of over 3 miles, all while maintaining perfect stability in ocean swells. Traditional salvage operations worked in shallow water, maybe a few hundred feet deep. The deepest salvage operation in history had recovered objects from just over 1,000 feet. Project Azorian was proposing to work at depths 16 times greater than anything previously attempted. The engineering challenges were so extreme that many experts believed the project was impossible. The pressure at 16,800 feet is crushing, literally. Every square inch of surface area experiences pressure of 760 pounds per square inch. A human body would be compressed to the size of a marble instantly. Any equipment sent to that depth had to be built like a spacecraft, but instead of protecting against the vacuum of space, it had to withstand pressure that could crush steel. But pressure was just the beginning of their problems. The ocean at that depth is perpetually dark and near freezing. Ocean currents at the surface could be completely different from currents at the bottom, creating complex three-dimensional flow patterns that could twist and snap any lifting cable. The submarine itself might have broken apart during its descent or deteriorated during its time on the ocean floor. The CIA needed a cover story, and it had to be believable enough to fool Soviet intelligence agencies that would certainly be watching. The story they chose was brilliant in its audacity: deep-sea mining. In 1970, there was growing interest in harvesting manganese nodules from the ocean floor. These potato-sized lumps contained valuable metals like nickel, copper, and cobalt. Several companies were seriously investigating the commercial potential of deep-sea mining. The beauty of this cover story was that it explained everything. Why would someone build a massive ship with advanced positioning systems? Deep-sea mining. Why would they need equipment capable of working at extreme depths? Deep-sea mining. Why would they need to lift heavy objects from the ocean floor? Deep-sea mining. The cover story was so perfect that it fooled not just the Soviets, but most of the American engineers working on the project. The CIA approached Howard Hughes, the eccentric billionaire known for his aerospace and engineering ventures. Hughes was perfect for the role. He had the financial resources to fund such an ambitious project. He had a reputation for pursuing seemingly impossible engineering challenges. Most importantly, he was known for his obsessive secrecy, which meant that unusual security measures around the project wouldn't raise suspicions. Hughes agreed to be the public face of the operation, lending his name and reputation to what the world would know as a commercial deep-sea mining venture. In reality, Hughes Tool Company became the front organization for the most expensive intelligence operation in history. The budget was classified, but estimates suggest the project cost over $800 million in 1970s money, equivalent to over $4 billion today. The ship they would build needed to be unlike anything that had ever existed. It would need dynamic positioning systems to hold it perfectly steady over a single point in the ocean, even in rough seas. It would need a moon pool, a massive opening in the hull that would allow equipment to be lowered directly into the ocean. Most importantly, it would need a lifting system capable of reaching the ocean floor and returning with a nuclear submarine. The engineering team knew they were attempting something that pushed the boundaries of physics and materials science. But they also knew that success would give the United States an unprecedented intelligence advantage. The Cold War was at its height, and both superpowers were locked in a technological arms race where any advantage could tip the balance of power. As we'll see in the next chapter, the solution they developed was so ingenious that it would revolutionize marine engineering forever. But first, they had to convince the world that Howard Hughes had suddenly developed an interest in mining the ocean floor. Howard Robert Hughes Jr. was already a legend by 1970. The heir to a tool company fortune, he had transformed himself into a movie producer, aviation pioneer, and aerospace manufacturer. He held multiple world airspeed records, had produced Hollywood blockbusters, and had built some of the most advanced aircraft of World War II. He was also famously reclusive, conducting business through intermediaries and rarely appearing in public. This combination of technical brilliance, unlimited resources, and obsessive secrecy made Hughes the perfect frontman for Project Azorian. When Hughes Tool Company announced its entry into deep-sea mining, the business world took notice but wasn't surprised. Hughes had a history of pursuing ambitious technological ventures that others considered impossible. The public story was carefully crafted and entirely plausible. Hughes had become interested in the commercial potential of manganese nodules, those metal-rich lumps scattered across the deep ocean floor. Scientists estimated that the Pacific Ocean floor contained trillions of these nodules, representing a virtually unlimited supply of valuable metals. The challenge was developing technology to harvest them economically. Hughes Tool Company announced that it would build the most advanced deep-sea mining vessel ever conceived. The ship would use revolutionary technology to locate, collect, and process manganese nodules from depths previously considered unreachable. The project would require years of development and hundreds of millions of dollars in investment, but the potential profits were enormous. To make the cover story convincing, Hughes Tool Company actually conducted legitimate research into deep-sea mining. They hired real oceanographers and marine geologists. They published scientific papers about manganese nodule distribution and composition. They filed patents for deep-sea mining equipment. The cover story wasn't just a lie. It was a fully functional business venture that happened to conceal the real purpose of the ship. The ship itself would be called Hughes Glomar Explorer, combining Hughes's name with Glomar, a contraction of Global Marine, the drilling company that would actually build the vessel. Global Marine had extensive experience with offshore drilling platforms and specialized in marine engineering projects. Their involvement added credibility to the mining story while providing the technical expertise needed for the real mission. Construction began at Sun Shipbuilding and Dry Dock Company in Chester, Pennsylvania in 1971. The shipyard workers were told they were building a revolutionary deep-sea mining vessel, and most of them believed it. The ship's unusual design features were explained as necessary for the mining operation. The massive moon pool was for lowering mining equipment. The advanced positioning systems were for maintaining precise location over mining sites. The heavy lift capabilities were for bringing up loads of manganese nodules. Soviet intelligence agencies were certainly watching the project, but the cover story held up under scrutiny. Deep-sea mining was a legitimate and growing field. Several other companies were developing similar technologies. Hughes had the financial resources and technical expertise to pursue such a venture. Most importantly, the ship's capabilities, while impressive, seemed reasonable for commercial deep-sea mining operations. The media coverage of the project focused on its commercial potential and technological innovation. Business magazines wrote about the future of deep-sea mining. Engineering journals analyzed the ship's advanced systems. Environmental groups debated the ecological impact of harvesting the ocean floor. Nobody suspected that the ship was actually designed to steal a Soviet submarine. Hughes himself played his role perfectly, maintaining his characteristic secrecy while occasionally making statements about the project's commercial potential. He spoke about revolutionizing access to ocean resources and establishing American leadership in marine technology. His public statements were carefully crafted to support the mining story while revealing nothing about the ship's true purpose. The cover story was so effective that it fooled not just foreign intelligence agencies, but most of the American government as well. Only a handful of people knew the ship's real mission. Engineers working on specific components were told only what they needed to know to complete their tasks. The compartmentalization was so complete that some engineers didn't learn the truth until decades after the project ended. But building a convincing cover story was the easy part compared to the engineering challenges they faced. The ship they were designing had to perform tasks that had never been attempted before, using technologies that didn't yet exist. As we'll see in the next chapter, creating Hughes Glomar Explorer would require innovations that pushed marine engineering to its absolute limits. What fascinates me most about this cover story is how it demonstrates the power of hiding in plain sight. Sometimes the best way to keep a secret is to tell everyone a different truth. Do you think such an operation could be kept secret in today's connected world? Share your thoughts in the comments. Hughes Glomar Explorer was 618 feet long, making it longer than 2 football fields placed end to end. It displaced 50,000 tons when fully loaded, making it one of the largest ships in the world. But size alone wasn't what made it revolutionary. The ship incorporated technologies that wouldn't become standard in marine engineering for decades. The most critical innovation was the dynamic positioning system. Traditional ships use anchors to maintain position, but anchors are useless in water 3 miles deep. Instead, Hughes Glomar Explorer used a computer-controlled system of thrusters that could automatically adjust the ship's position to within a few feet, even in rough seas. This technology was so advanced that it wouldn't become common on commercial vessels until the 1990s. The heart of the ship was the moon pool, a massive opening in the hull that measured 199 feet long by 74 feet wide. This opening allowed equipment to be lowered directly into the ocean without being affected by the ship's movement. The moon pool was surrounded by massive steel doors that could be opened and closed as needed, and the entire area could be flooded or drained depending on operational requirements. Above the moon pool was the derrick, a steel tower that rose 225 feet above the ship's deck. This wasn't just a crane. It was a precision lifting system capable of handling loads of thousands of tons while maintaining perfect control. The derrick could extend and retract a lifting system made of specially designed steel pipe sections, each 60 feet long and weighing several tons. The pipe string, as it was called, was an engineering marvel in itself. Traditional drilling pipe couldn't handle the stresses involved in lifting a submarine from such depths. The engineers developed a new type of pipe that was stronger and more flexible than anything previously used. Each section had to be perfectly manufactured because a failure of any single section would doom the entire mission. The ship's hull was designed to handle stresses that no ship had ever experienced. When lifting a 5,000-ton load from 3 miles down, the forces involved are enormous. The ship had to be strong enough to support this load without breaking apart, but flexible enough to handle the dynamic forces created by ocean waves and currents. The hull design incorporated advanced materials and construction techniques that pushed the boundaries of naval architecture. The power systems were equally impressive. The ship needed massive amounts of electrical power to operate its positioning thrusters, lifting systems, and life support equipment. It was equipped with multiple diesel generators capable of producing enough electricity to power a small city. Backup power systems ensured that critical operations could continue even if the main generators failed. Environmental control was another major challenge. The ship would be operating in the middle of the Pacific Ocean for months at a time, completely self-sufficient. It needed freshwater production systems, waste processing facilities, and air conditioning systems capable of maintaining comfortable conditions for a crew of 170 people. The ship was essentially a floating city designed to operate independently for extended periods. The navigation and communication systems were state-of-the-art for their time. The ship used satellite navigation, which was still experimental in the early 1970s. It had multiple communication systems for maintaining contact with shore-based controllers, as well as secure communication equipment for coordinating with CIA personnel. All of these systems had to be disguised as commercial equipment to maintain the mining cover story. Perhaps most impressively, all of these advanced systems had to work together seamlessly. The dynamic positioning system had to coordinate with the lifting system to maintain precise control over the pipe string. The power systems had to provide stable electricity even when massive loads were being lifted. The environmental systems had to continue operating regardless of what else was happening on the ship. The engineering team faced challenges that had no precedent in marine engineering. They were essentially inventing new technologies while building the ship that would use them. Computer modeling was primitive in the early 1970s. So many design decisions had to be based on theoretical calculations and educated guesses. The margin for error was essentially zero, because failure would mean losing the submarine forever and exposing the entire operation. Testing was another major challenge. How do you test a system designed to lift submarines from the ocean floor without revealing what you're actually planning to do? The engineers developed elaborate test procedures that could verify the ship's capabilities while maintaining the mining cover story. They tested individual components separately and used computer simulations to predict how the complete system would perform. The construction process took over 3 years and required the coordination of dozens of contractors and suppliers. Each component had to be manufactured to exacting specifications, and quality control was critical at every stage. The slightest defect in any component could cause a catastrophic failure during the actual mission. By 1973, Hughes Glomar Explorer was nearing completion, and it was already clear that the ship represented a quantum leap in marine engineering capabilities. But the most challenging part of the project was still ahead: designing and building the mechanical system that would actually grab the submarine from the ocean floor. At the bottom of that 3-mile-long pipe string hung the most sophisticated piece of machinery ever lowered into the deep ocean. The engineers called it Clementine, and it was essentially a giant mechanical claw designed to grab a nuclear submarine and hold it securely during a 3-mile journey to the surface. Clementine was massive, measuring 180 feet long and weighing over 2,000 tons. It was built like a steel cage that could open and close around the submarine. The claw had multiple hydraulic arms that could adjust to grip the submarine's hull at various points, distributing the lifting forces to prevent the submarine from breaking apart during recovery. The design challenges were staggering. The claw had to be strong enough to lift a 5,000-ton submarine, but precise enough to grip it without causing damage that might destroy valuable intelligence materials. It had to operate in total darkness under crushing pressure, guided only by sonar and remote cameras. Most importantly, it had to work perfectly on the first attempt because there would be no second chance. The hydraulic systems that operated Clementine were engineering marvels in themselves. Hydraulic fluid had to be pumped down 3 miles of pipe to operate the claw's mechanisms. The pressure required was enormous, and any leak in the hydraulic system would render the claw inoperable. The engineers developed new types of seals and fittings that could withstand the extreme pressures involved. Clementine was equipped with multiple cameras and sonar systems to help operators locate and position the claw around the submarine. These systems had to operate in conditions where no natural light existed, and visibility was measured in inches rather than feet. The cameras used powerful lights that could penetrate the murky water near the ocean floor, while sonar systems created 3-dimensional maps of the submarine's position and condition. The control systems for Clementine were equally sophisticated. Operators on the surface had to control the claw's movements with precision, despite the 3-mile distance and several-second delay in communications. The control systems used early computer technology to help compensate for these delays and provide operators with real-time feedback about the claw's position and status. One of the most challenging aspects of Clementine's design was predicting how the submarine would react to being lifted. After years on the ocean floor, K-129 might have settled into the sediment or suffered structural damage that could cause it to break apart when disturbed. The claw had to be designed to handle various scenarios, from lifting an intact submarine to recovering pieces of a broken hull. The materials used in Clementine's construction were specially selected for their strength and corrosion resistance. The deep ocean is incredibly corrosive, and any metal that isn't properly protected will quickly deteriorate. The engineers used advanced alloys and protective coatings that could withstand months of exposure to seawater under extreme pressure. Testing Clementine presented unique challenges. The claw was too large and complex to test in any existing facility, and testing it at operational depth would reveal the project's true purpose. Instead, the engineers conducted extensive computer simulations and tested individual components separately. They built scale models to test the basic principles and used mathematical models to predict how the full-size system would perform. The assembly process for Clementine was incredibly complex. The claw was too large to build in one piece, so it had to be assembled from multiple sections that were manufactured separately and then joined together. Each joint had to be perfect, because any weakness could cause the entire system to fail during the lifting operation. The engineers also had to design backup systems for every critical component of Clementine. If the primary hydraulic system failed, backup systems could take over. If the main gripping arms malfunctioned, secondary arms could maintain hold of the submarine. The redundancy was essential because any failure during the mission would mean losing both the submarine and the expensive recovery equipment. Perhaps most impressively, Clementine had to be designed to fit through the moon pool opening in Hughes Glomar Explorer's hull. This meant that the claw had to be collapsible, able to fold into a compact configuration for lowering through the ship, then expand to its full size once it reached the ocean floor. The mechanical systems required to accomplish this transformation were incredibly complex. The final design of Clementine represented the culmination of years of engineering innovation. It incorporated technologies that wouldn't become common in deep-sea operations for decades. The claw was essentially a deep-sea robot, capable of performing complex manipulation tasks under conditions that would instantly kill any human operator. By 1974, both Hughes Glomar Explorer and Clementine were ready for their ultimate test. The ship and its revolutionary lifting system represented the most advanced marine technology ever created. But all of this engineering brilliance would be meaningless if they couldn't successfully locate and recover K-129 from its resting place on the Pacific Ocean floor. The audacity of what they were attempting still amazes me. Building a giant mechanical hand that could reach 3 miles into the ocean and delicately pluck up a submarine. What do you think about this level of engineering ambition? Was it brilliant innovation or dangerous overreach? Let me know in the comments. On July 4, 1974, Hughes Glomar Explorer departed Long Beach, California on what the world believed was its maiden deep-sea mining voyage. The ship's crew of 170 included legitimate mining engineers and oceanographers who genuinely believed they were testing revolutionary mining technology. Only a handful of CIA operatives and senior engineers knew the ship's true mission. The journey to the target site took several days, during which the crew conducted what appeared to be routine mining surveys. They deployed equipment to map the ocean floor and test the ship's positioning systems. These activities served the dual purpose of maintaining the mining cover story while allowing the crew to practice the complex procedures they would need for the actual recovery operation. Soviet surveillance was intense from the moment the ship left port. Soviet intelligence agencies had been monitoring the project since construction began, and they deployed ships and aircraft to observe Hughes Glomar Explorer's activities. The CIA had anticipated this surveillance and had developed elaborate procedures to conduct the recovery operation without revealing its true nature. When the ship reached the target coordinates, it began the delicate process of positioning itself directly over K-129's resting place. The dynamic positioning system had to maintain the ship's location within a few feet while accounting for ocean currents, wind, and waves. This positioning process took several hours and required constant adjustments to keep the ship precisely aligned with the submarine below. The first phase of the operation involved lowering cameras and sonar equipment to locate and assess the submarine's condition. After 6 years on the ocean floor, K-129 had settled into the sediment and suffered significant deterioration. The submarine's hull was intact, but it had broken into several sections during its descent to the bottom. This discovery forced the mission planners to revise their recovery strategy. Lowering Clementine to the ocean floor took over 20 hours. The massive claw had to be carefully guided down through 3 miles of water while the ship maintained perfect position above. Ocean currents at different depths tried to push the claw off course, requiring constant adjustments from the surface operators. The psychological pressure on the crew was enormous, knowing that years of planning and hundreds of millions of dollars depended on the success of this operation. When Clementine finally reached the ocean floor, the operators began the painstaking process of positioning it around the submarine's hull. Using cameras and sonar, they guided the claw into position and slowly closed its arms around the submarine's midsection. The hydraulic systems operated flawlessly, and within several hours, Clementine had a secure grip on its target. The lifting operation began slowly, with Clementine rising just a few feet at a time while operators monitored the submarine's structural integrity. The initial stages went smoothly, and it appeared that the recovery would be successful. The submarine remained intact as it rose through the first 1,000 feet of its journey to the surface. But at approximately 5,000 feet below the surface, disaster struck. The submarine's hull, weakened by years of corrosion and the stresses of lifting, began to break apart. The forward section, containing the nuclear warheads and most valuable intelligence materials, separated from the rest of the submarine and fell back to the ocean floor. Clementine managed to retain its grip on the aft section, which contained the submarine's nuclear reactor and some crew quarters. The mission controllers faced a critical decision. They could attempt to recover the fallen section, but this would require lowering Clementine back to the ocean floor and starting the entire process over again. The risk was enormous, and Soviet surveillance ships were becoming increasingly suspicious of Hughes Glomar Explorer's activities. After intense deliberation, the decision was made to continue with the partial recovery. The remaining section of K-129 was successfully lifted into Hughes Glomar Explorer's moon pool. The recovery operation had taken over 6 days, during which the ship had to maintain perfect position while conducting one of the most complex engineering operations ever attempted. Despite losing the most valuable part of the submarine, the mission was considered a partial success. The recovered section contained valuable intelligence about Soviet nuclear reactor design and submarine construction techniques. More importantly, it proved that the technology developed for Project Azorian actually worked. Hughes Glomar Explorer had successfully lifted a multi-thousand-ton object from the deepest parts of the ocean, demonstrating capabilities that wouldn't be matched for decades. The crew conducted what appeared to be normal mining operations for several more days before returning to port. The recovered submarine section was secretly transferred to CIA facilities for detailed analysis, while the world continued to believe that Hughes Glomar Explorer was simply testing deep-sea mining technology. The mission's secrecy was maintained for over a year until investigative journalists began uncovering details of the operation. Even then, the full extent of Hughes Glomar Explorer's capabilities and the sophistication of Project Azorian remained classified for decades. The ship had proven that with sufficient resources and engineering innovation, even the most impossible tasks could be accomplished. The partial failure of the mission highlighted both the incredible ambition of the project and the inherent risks of pushing technology to its absolute limits. The engineers had succeeded in creating a system capable of reaching into the deepest parts of the ocean and recovering massive objects, but they had also learned that some challenges remained beyond human capability to fully control. Hughes Glomar Explorer's story didn't end with Project Azorian. After the submarine recovery mission, the ship faced an uncertain future. It was too advanced and too expensive to operate as a commercial mining vessel, but its capabilities were too valuable to simply scrap. The ship became a symbol of both the possibilities and limitations of Cold War-era engineering ambition. The technologies developed for Hughes Glomar Explorer revolutionized marine engineering in ways that are still being felt today. The dynamic positioning systems pioneered on the ship became standard equipment on offshore drilling platforms and research vessels. The heavy lift capabilities demonstrated by Clementine led to advances in deep-sea construction and salvage operations. The precision control systems developed for the mission influenced everything from underwater robotics to space exploration. Perhaps most significantly, Project Azorian proved that the boundaries of engineering possibility were far more flexible than previously believed. The project demonstrated that with sufficient resources, innovative thinking, and meticulous planning, engineers could accomplish tasks that seemed impossible. This lesson influenced countless subsequent projects, from deep-sea exploration to space missions. The ship itself had several more careers after its CIA mission. In the 1980s, it was converted for legitimate deep-sea mining research, finally fulfilling its original cover story. The ship was used to test actual manganese nodule recovery systems and contributed to our understanding of deep ocean mineral resources. Later, it was used for various scientific research missions, taking advantage of its unique capabilities for deep-sea operations. The secrecy surrounding Project Azorian created lasting changes in how intelligence operations are conducted and concealed. The success of the Hughes cover story demonstrated the power of hiding covert operations within legitimate commercial ventures. This approach has been used in numerous subsequent intelligence operations, though none have matched the scale and audacity of Project Azorian. The engineering innovations developed for the project had impacts far beyond marine operations. The computer control systems pioneered for Clementine influenced the development of industrial robotics and automated manufacturing. The materials science advances made for the deep-sea environment contributed to improvements in aerospace and nuclear engineering. The project management techniques developed for coordinating such a complex operation became models for large-scale engineering projects. From a geopolitical perspective, Project Azorian marked a turning point in Cold War intelligence operations. The project demonstrated that technological superiority could provide intelligence advantages that traditional espionage methods could never achieve. This realization led to increased investment in technical intelligence capabilities and influenced the development of satellite reconnaissance and electronic surveillance systems. The partial failure of the submarine recovery also provided valuable lessons about the limits of engineering ambition. Despite all the advanced technology and careful planning, the mission couldn't overcome the fundamental challenge of lifting a deteriorated object from extreme depths. This experience influenced subsequent deep-sea operations, leading to more conservative approaches and better understanding of material limitations in extreme environments. Hughes Glomar Explorer's legacy extends into modern deep-sea exploration and exploitation. The techniques developed for the project influenced the design of modern deep-sea mining systems, underwater construction equipment, and scientific research vessels. The ship's dynamic positioning systems became the foundation for modern offshore drilling operations, enabling the extraction of oil and gas from increasingly deep waters. The project also highlighted the importance of international cooperation and regulation in deep-sea operations. The secrecy surrounding Project Azorian contributed to the development of international treaties governing deep-sea activities and established principles for the peaceful use of ocean resources. These agreements continue to influence modern deep-sea exploration and commercial activities. Perhaps most importantly, Hughes Glomar Explorer demonstrated that the intersection of engineering innovation and human ambition could produce results that seemed impossible. The project showed that with sufficient determination, resources, and technical skill, engineers could reach into the deepest parts of the Earth and accomplish tasks that previous generations could only imagine. Today, as we face new challenges in deep-sea exploration, space exploration, and environmental protection, the legacy of Hughes Glomar Explorer continues to inspire engineers and innovators. The ship proved that the phrase, "impossible," is often just another engineering challenge waiting to be solved. The story of Hughes Glomar Explorer reminds us that the most significant technological advances often come from attempting the impossible. Whether it's reaching into the deepest parts of the ocean or exploring the farthest reaches of space, human progress depends on engineers willing to push beyond the boundaries of what seems possible. What strikes me most about this incredible story is how it represents the pinnacle of human engineering ambition during the Cold War era. In an age before computer modeling and advanced materials, a team of engineers designed and built a ship capable of performing tasks that still seem impossible today. What do you think? Could such an ambitious project be accomplished in secret in our modern, connected world? And what impossible challenges do you think today's engineers should be tackling? Share your thoughts in the comments below. Thank you for joining me on this journey into the archives of unrealized technologies and grand failures. If you enjoyed this deep dive into Cold War engineering, make sure to subscribe to Never Built for more stories of ambitious projects that push the boundaries of human capability. Until next time, keep questioning what's possible.